Okay, hello everyone. Let's start with the first tutorial on neural architecture search by Colin and Dave.
All right. Thank you very much. Thanks everyone for choosing our tutorial, even though there's no food in this room. And yeah, thanks a lot to the organizers. It's really exciting to be at this AutoML conference. I know I really joined the area in 2019, so I'm looking forward to meeting everyone in person for the first time. And yeah, so we are giving a tutorial on neural architecture search, foundations and trends. I'm giving the first part, and then I'll hand it off to Day halfway through. There'll also be time for questions in the middle. And this is a trick I got from Frank. My slides are already up on my website, crwhite.ml, with hyperlinks. So if you want to follow along, you can click the links of all the papers I talk about. Also, feel free to ask me any questions throughout the tutorial. Okay. Okay, there we go. 1 second. Caret press. Sorry about that. Okay, here we go. So neural architecture. Okay, so machine learning is actually, let me try to move this thing. Maybe I'll just put it down here. Okay. So neural architecture search, so machine learning is a story of automation. This image is from the 1950s, the perceptron algorithm. And back then, it really took quite a lot of effort to train just one machine learning model and make predictions. But nowadays in 2022, what we do is we open our terminal and import PyTorch and then load a pre-trained model. So we really come a long way in the last 70 years in automating this whole process and making it much easier for ourselves. And in particular, one of the big leaps in terms of automation happened around 2012 with the deep learning boom, where now people spend way less time on manual feature engineering because it all happens automatically with neural networks. However, we are not quite done with this automation because these architectures are very complex. So this is GoogleNet, which is from 2014. And as you can see, the operations and the network is extremely complex here. It took experts at Google's time to create this architecture. And here's another example from 2016. This is DenseNet. Once again, there are quite a lot of magic numbers here that had to be painstakingly found to be the right numbers. Yeah, the architectures are just getting more and more complex over time. So both of these, the previous network I showed and this network, were designed for ImageNet, which is perhaps the most well-known benchmark in machine learning, or one of them. So this is a plot of ImageNet, the world records of ImageNet over time. And something really interesting happened around 2017, which is that for the first time ever, the world record on ImageNet was held by an architecture that was searched automatically. Okay, so the machines beat the humans. And nowadays in 2021 and beyond, with the EfficientNet line of architectures, it's really the searched architectures are the ones that are outperforming architectures that are fully human designed. But to be fair, there's still quite a lot of human effort. It's really a joint effort at this point. So this is the EfficientNet architecture. On the left are all the magic numbers that were found by search algorithms, and on the right are the specialized building blocks designed by humans. Okay. Yeah, so the algorithms that find these architectures are algorithms for neural architecture search. This is the process of automating the design of neural architectures for a given data set. And this field has seen quite a lot of attention over the last few years. Specifically, in the last 2 years, there's been more than 1,000 papers in this area. So yeah, quite a lot of activity, and it's a great time to be in this field of research. Okay, so the slides I showed before was evidence that neural architecture search can do really well on the most popular benchmarks, but neural architecture search also does really well on brand new data sets that we rarely see or have never seen before. So there's a nice line of work by Amit Talwalkar and his group that show NAS algorithms can work well on very diverse tasks, such as protein folding, PDE solving, astronomy imaging, and so on. Yeah, and today neural architecture search is being applied to graph neural networks, GANs, dense prediction, and adversarial robustness. Okay, and just a bit more motivation. So NAS is also really good at constrained or multi-objective optimization. So one of the biggest success stories in neural architecture search is fitting very high performing models onto edge devices. For example, this is a MobileNet v3, and the tables on the right were all the numbers found by the NAS algorithms, and this is a Pareto curve. And I believe Dave will be talking even more about this in part 2. Okay, so I gave quite a lot of motivation. So this is just a summary. So NAS can do well on the most widely used benchmarks like ImageNet, also on new data sets that we haven't seen before, and also on fitting high performing models onto edge devices. And another thing is that NAS is really helping to democratize deep learning. So even though the first NAS algorithms took thousands of GPU hours to run, the most efficient techniques today take just a few GPU hours. So really this allows anybody who has a few cloud credits to go and run some of these NAS algorithms and get a very high performing model, high-performing deep learning model for their data set. So these techniques are really helping anyone get into deep learning. Okay, so now I wanted to give a brief history. So yeah, this has been studied at the very least since the late 1980s, but it saw a huge resurgence in 2016 after deep learning itself saw a resurgence. So Zof and Le really had a paper that started a lot more research in neural architecture search. In the first few years of this resurgence, the majority of the techniques focused on black box optimization-based techniques, but there was an impactful paper in 2018, the DARTS algorithm, which really caused the majority of papers in the future to be more one-shot or weight-sharing based. And I will talk a lot more about what these two terms mean throughout the rest of the tutorial. And yeah, other things of note I put on this timeline is the first tabular benchmark came out in 2019. We will talk a lot more about this and best practices. And I also added DARTS PT because it won an outstanding paper award at iClear 2021, which is just another data point that this field is really mainstream and getting a lot of attention. Okay. So I gave like an informal definition before, now a bit more formal of a definition of NAS. So the first thing we need to do is define a search space. This is just a large set of architectures, a finite set of architectures. And then we search to find the architecture that maximizes validation accuracy after training it to minimize training loss. So in other words, it's like a bi-level optimization problem where for each architecture, we want to look at its validation accuracy after fully training, and then find the architecture with the highest validation accuracy that we can. Of course, there are a lot of variants of this definition. If, for example, like constrained optimization or breaking out of the bi-level optimization approach, but this is like a good definition to keep in mind. Okay, and a useful taxonomy to keep in mind are these 3 pillars of NAS: the search space, search strategy, and performance estimation strategy. Okay, so the way that many NAS algorithms work is that once we define our search space of architectures, we have some algorithm that searches, and it iteratively picks an architecture that it as a candidate, and then we estimate the performance somehow, and then feed that back into the algorithm, and then it picks the next candidate. This works particularly well for black box optimization based algorithms. For one-shot and weight sharing algorithms, it's a bit harder to separate the search strategy from the performance estimation. So that's just a note about these 3 pillars. But we'll talk a lot more about the weight sharing techniques a bit later. Okay, so that comes to the end of my motivation and introduction. So now I'll get a bit more into the meat of the talk. I'll talk a lot about search spaces and talk about the most common types of search spaces, as well as how to encode the architectures. And then I'll also discuss black box optimization methods and performance prediction. And then in the second half, I think the topics Day will cover include weight sharing methods, transformers, best practices, and future directions. Okay. So the search space. So I think this is arguably the most important part of NAS for a couple of reasons. One is that it's really what distinguishes NAS from other areas of AutoML, such as hyperparameter tuning, where sometimes the search strategies overlap between NAS and HPO, but the search space, that's really unique to neural architecture search. And another reason I think search spaces are really important is that if you spend a lot of time to design a good search space, then even a very simple algorithm like random search can do pretty well. We see some examples of that in the field. Okay. So at the heart of designing the search spaces is this big trade-off we have to make between exploration and exploitation. And by that, I mean, I can encode my human bias. I can say like, oh, I'm doing a computer vision task. I know convolutions and pooling operations work really well. So I can add a lot of architectures that have these sorts of operations. On the other hand, I can just give no human bias at all and have like a very enormous search space, which might be truly novel that I've never even thought of before that works better. However, it's much more computationally intensive to run on such a big search space. So on the slide, I have sort of two of the extremes. On the exploration side, we have AutoML0, which searched over just the most low-level operations like multiplying vectors together, and so like this search really could have found anything. They found that it showed like a primitive version of backpropagation, which is pretty interesting, but it takes so much compute time it didn't discover like the next transformer or anything. And on the other side, I have cell-based search spaces as like really exploit heavy that encodes a lot of human bias. Yes, and so when we have a search space like this, the average architecture does really well, but searching doesn't improve performance by that much since the search space is so much smaller. Okay, so this is the gist of search space design. Now I'll go over 3 of the most common types of search spaces. So first, I have macro search spaces. These are, in some sense, the simplest, the ones with the least constraints. Typically, what we do is define a set of operations that we want, like convolution, pooling, or something like that. And then we allow our algorithm to iteratively add more and more operations in a chain, or maybe add some skip connections, or add some more complex topology. So the image on the right is architectures found by NASBot. Sometimes a chain structured architecture worked the best for some data sets, and sometimes a more complex directed graph worked better. Okay, so these were sort of the first types of search spaces that people used in the resurgence of NAS. And then next, okay, so next are possibly the most popular type of search spaces, which are cell-based search spaces. So the problem with macro search spaces is that even these are so big that it takes quite a lot of compute power to search over like a large architecture that could get strong performance. So the solution that people came up with is cell-based search spaces, which gives us the best of both worlds, because the idea is that we search over a relatively small cell of maybe like at most 10 operations, but then we stack it many times on top of itself so that we get like a very powerful, large, deep network. So the search computation is tractable, but we still get like a very high performing architecture in the end. And this is sort of the intuition is borrowed from human designed architectures that tend to have quite a lot of repeating parts throughout the architecture. Okay, so yeah, these are used quite a lot in NAS research and in practice because the search algorithms can find strong architectures, and we get the full power of a big architecture. So these are the image here is two popular cell-based search spaces. There are a couple of ways to do it. We can define the nodes or the edges of the graph as operations. Different work does both methods, and then we search over the operations for each location an operation is at, and also search over what sort of connections there are between the nodes. Okay. And finally, the third type of search space I'll talk about are hierarchical search spaces. So these are, I believe these are an up and coming technique because they still the computation is relatively tractable. There are not so many hyperparameters, but they can be very expressive and have a very diverse set of architectures. So the idea is that for cell-based search spaces, we had a fixed skeleton, like a human designed, like, okay, put like 20 cells here and connect them in this way. But in hierarchical, we add the skeleton, we add hyperparameters to the skeleton. So our NAS algorithm can also search over the backbone of the architecture itself. And so what I just described would be a two-layer hierarchical search space where we search over the cell and then over the backbone. But we could also have more and more layers, like search over like the lowest primitives, like the operations, and then search over the cell, and then search over some intermediate structure, and then the final structure. And so yeah, this is a really strong type of search space because it gets a great trade-off between computational tractability, but also finding truly diverse or novel architectures. Okay, so next I wanted to talk about NAS benchmarks. So Day will also cover best practices in the second part, but since I'm already talking about search spaces, I'll give an overview of the different NAS benchmarks. Okay, so before 2019, there was a problem in the field of NAS, and the problem is that these techniques take quite a lot of time to run. Like even an efficient technique might take like a day in GPU power or something like that. And so it's quite challenging to run your method many times. Like if we want to run this method 10 times to get a robust estimate of performance, it takes a lot of compute. And furthermore, if we want to compare our method to 10 other methods and run each of those 10 times, then it's a really high amount of compute. So the answer was to release tabular NAS benchmark. So this was the team at Freiberg and Google. What they did is define a medium-sized search space of size 400,000. and then evaluated every single architecture in the search space 3 times each, and then saved the final accuracies in a lookup table that so now we have this lookup table of all the accuracies. And then I can simulate my own NAS experiment where every time my algorithm wants to train an architecture, I just look up the final accuracy in the table and then add the time it would have taken to train into the runtime of my algorithm. So it allows me to simulate my algorithm, but just in minutes rather than days. And so this allows me to run 100 trials of my algorithm or more very quickly, and also compare it to many other algorithms. So yeah, NAS'22 made a much more scientifically principled experiments to be much more accessible. Since then, there have been quite a lot of NAS benchmarks that have been released that all look at various data sets and tasks. I just gave an overview here. I'll talk about a few more of the different types of benchmarks. So the problem with tabular NAS benchmarks is that we cannot create one for very large search spaces. For example, darts, the Dart search space is used quite a lot, but it's size 10 to the 18. So it's just not nearly possible to create a lookup table of all the accuracies of the trained architectures. But a solution that again the Freiburg team came up with is to create a surrogate benchmark. So the idea here is to take 60,000 randomly sampled architectures or a stratified sample of architectures, and then train a model that predicts the performance of all the rest of the architectures in the search space. And there's an interesting thing that happens that I have on the right here, which is that surrogate benchmarks are actually have less error than tabular benchmarks. And the reason is that even tabular benchmarks, where we just train all the architectures 3 times each, there still can be a variance because there's noise when you train any individual architecture. So even if we train them 3 times each, there's still a bit of noise that we have, like if we average the 3 architectures. But with surrogates, since the surrogates are so powerful, we actually get less noise than even an average of 3 seeds of architectures. Of course, when we actually run experiments, we want to add back the noise because we want it to be realistic. So we just model, we can also model the noise of the architecture. Okay, one more development I'll talk about surrogate NAS benchmarks is so the surrogate NAS benchmark is great, but we can only get back the final accuracy of each architecture. So say I have a NAS algorithm that's a bit more complex, like it's a white box method that does learning curve extrapolation or something, we wouldn't be able to use this surrogate NAS benchmark. And but there's a follow-up work that actually showed that we can use a surrogate to predict the entire learning curve. And so that's this slide at the bottom here. And the idea here is that we can use dimensionality reduction on the learning curves to have some sort of smooth learning curve with less noise, and use our surrogate model to predict these smooth learning curves. But then we also model the noise distribution, and then we add back the noise to the final learning curve to output a realistic noisy learning curve. So the takeaway is that we have surrogate NAS benchmarks that we can simulate NAS experiments on very large search spaces, even if we have white box methods. Okay. So yeah, once again, there are all these NAS benchmarks now that make research more principled. But one other problem is that all these benchmarks are created by different people in different repositories, and some of them even use like PyTorch versus TensorFlow. So it's hard to use each of these in all of our projects. But there's an answer to that as well. So just earlier this year, NAS Bench Suite was released, which brings 25 of these benchmarks into a single repository or a single framework. So now we can just implement our algorithm once in one place and then immediately run it on 25 different tasks. And in NAS Bench Suite, we already found some interesting results. For example, it's quite common for researchers to evaluate their algorithms on NAS Bench 101 and 201 only. But what we showed is that the correlations do not match. If we run algorithms on just 101 and NAS Bench 101 and 201 versus all the rest of the 25 tasks, we really see quite different trends in what the best algorithms are. So this is more evidence that we should really run our algorithms across a very diverse set of tasks in order to get the most realistic estimate of what the performance is of our algorithm. Okay. And then one more note I wanted to make when talking about search spaces is so we have our search algorithm, and in order for our search algorithm to work, we need to encode these architectures. So we need to have some way of passing the architecture to the search algorithm, or encode the architecture. So since the architectures are directed acyclic graphs, one of the most natural ways to do this is by looking at the adjacency matrix. That's what's displayed here. I'll also have to pass a list of the operations because it's a labeled graph. However, some works showed that even small changes to the way that we encode architectures could make a very big difference in performance. So for example, even changing the encoding from one hot to categorical can drastically change the performance of our algorithm. And so a couple of years ago, there's a study on encodings for NAS, and what the study did is identified a few common subroutines that most NAS algorithms make use of. For example, sampling an architecture at random, or perturbing an architecture, or training a predictive model, and looked at what the best encoding is for each of these subroutines. And the results are listed in this paper. I believe that for the first two subroutines, sample and perturb, an adjacency matrix-based encoding worked the best. But for a trained predictor model, a more interesting encoding like path-based or VAE-based encoding works better. Okay. So next, I'm finished talking about search spaces. Now I'll talk about black box optimization methods, and then at the end, performance prediction. Okay, so to start with talking about the search strategies, I want to talk about baselines. And what better baseline to start with than just random search? So of course, this is just the simplest possible algorithm where we randomly sample an architecture from the search space and then fully train it, and then continue to do this. But despite how simple it is, a surprising amount of works show that random search is quite competitive compared to other methods in the field. So yeah, we always want to compare our method to random search. And another pretty related sanity check is random sampling. So this is even simpler. Random sampling is just compute what the average accuracy of an architecture is in your search space when drawing these architectures at random. And so Yang et al. In 2019 showed that actually some algorithms don't actually outperform random sampling, where this dotted line here is the randomly drawn architecture, and so the algorithms we want to be above this line. Okay, so this is just a reminder that we always have to sanity check with random sampling and random search. Okay, so one more baseline that's always nice to run is local search, because a couple works 2 years ago also showed that local search is surprisingly quite competitive with some of the better NAS algorithms that are out there. But this is also a very simple algorithm, just 5 lines of code, where we pick an architecture and then evaluate all architectures in its neighborhood, and then find the best neighbor, and then recur and start the next iteration with that architecture. Okay, so now a bit more interesting algorithm is Bayesian optimization. And this is quite a natural method to use, because Bayesian optimization does very well for black box functions that are expensive to evaluate. That's why it's used quite heavily in both hyperparameter optimization and also neural architecture search. So I have here some of the most prominent works that use Bayesian optimization, and so Bayesian optimization is mostly used with a Gaussian process as the predictive model, but this does not scale well to high dimensions or high number of data points. So what people have done recently is to replace the Gaussian process with a neural network. And so now I'll explain what I mean in a bit more detail now. So we're all on the same page. In this algorithm, we start by in the first round, we might like randomly pick some architectures, and then we start this iterative process where we take all the architectures that we've fully trained so far, and then we use that as training data to create this model that takes in architectures as input and predicts their accuracy. So this is our model, and then in each iteration, we create a set of candidate architectures, and we predict their performance with this model. And then we might also get some uncertainty estimate of our predictions. And then we have some acquisition function to trade off exploration and exploitation. And then at the end, we pick the best architectures to evaluate to start the next iteration. Okay, but in this framework, there are quite a lot of decisions we need to make. For example, how do we encode the architectures? What model do we use? How do we calibrate the uncertainty of our model? And also which acquisition function to use? And then finally, how do we pick the candidates? So there are quite a lot of choices that need to be made. Yeah, so we had a work last year that ran a large study on all of these different components that I just mentioned, and really found the highest performing components for each part of the algorithm. So the result, at least for NASBench 101 and 201, was use of path encoding with an ensemble of neural networks and create a set of candidates by mutating the best architectures we found so far, and then use independent Thompson sampling as the acquisition function. Okay, and this created the bananas algorithm. Okay, so go ahead. Yeah.
Would the answers come out to be the same?
Oh yeah, great question. So Day asked if we ran this study again on NASBench Suite on all 25 tasks, would we get the same answers? So I haven't done that. I would expect that at the very least the path encoding would change, because I have intuition that works better for smaller cell-based search spaces, but not nearly as well for other search spaces. So probably something safer like adjacency coding would do better. Let me think. I also, since this work, there are other works that show boosted trees are a better model. So I guess, yeah, that is also slightly outdated. But I think the final two small mutations in Thompson sampling, those still would hold up well. Okay. Yeah, good question. Okay, so next, evolution is also used quite a lot in neural architecture search. So in 2018, a team at Google showed that regularized evolution can achieve state-of-the-art performance in neural architecture search. So the idea for this algorithm is that in each iteration, we maintain a population of architectures. Say we have like 50 architectures, and then they have some sort of tournament, which might involve like randomly picking architectures and then picking the best architectures from that random sample. And then we generate offspring from these strong architectures, for example, by just mutating the architectures. And then at the end of each iteration, we kill off the oldest architectures. Okay, so just this simple evolution-based method can achieve state-of-the-art performance. Yeah, there are many decisions for this for evolution as well. For example, like how do we sample the initial population? How do we do this tournament selection? And how do we create the offspring? And other works have also explored this, although I'm not sure there's actually one of these big studies that looks at all the different parts like there was in Bayesian optimization. Okay, so now I'm nearly finished with my time in part 1, and I will end by discussing performance prediction. Okay, so what I mean by performance prediction is any technique which predicts the relative accuracy of an architecture without fully training it. And so the way I'm presenting this, it's a subroutine that we might want to use in NAS. And really this can be used to speed up any NAS algorithm, either black box optimization or even weight sharing methods. They're being used quite a lot in many different NAS algorithms to improve performance. Okay, so, and yeah, here I have a Venn diagram of the many different types of predictors we might use. All of them have some sort of query function that takes an architecture as input and then outputs the predicted performance. And then some of them we might need to initialize with some sort of pre-computation. Okay, so there are a few different families of performance predictors. The first one, which I sort of talked about with Bayesian optimization, is model-based predictors. So this is any sort of model where we train it on training data that consists of fully trained architectures to take as input the architecture and then output a prediction of the architecture's accuracy. So people have tried Gaussian processes, neural networks, boosted trees, as well as graph neural networks and encodings as the type of model that works the best. Recently we had a study on different predictors, and we found that boosted trees often perform the best, especially if we train the model on a lot of data. But if we have less architecture, less training data, then some of the specialized approaches like graph neural networks or specialized encodings work better. Okay. And then another type of predictor is learning curve based predictions. So this is where, say we partially train an architecture, we get the learning curve, and then we try to extrapolate the rest of the learning curve. And we might try many different types of functions to see what models the learning curve the best. So there's also quite a lot of work in the best way to run learning curve extrapolation. It's sort of a challenging problem because the learning curves tend to be quite noisy in the early epochs, but there's a lot of interesting work that deals with this noise and can get estimates of the final learning curve. Okay, so in contrast to model-based predictors, these every individual query takes a lot of time because we need to partially train a neural network, but we don't need to get training data at the start. We can run these immediately for any new architecture. And then we can also combine the these two types of predictors. So we can have a model that takes in the architecture encoding as well as part of the learning curve, and then predicts the final accuracy. So these are very high performing because they combine the techniques of the two, but they're also very expensive to run because we need training data to set it up, and then in any new prediction we need to partially train the architecture. Okay, and finally, the last family I'll talk about are zero-cost proxies. So these are quite an interesting new technique in neural architecture search, where the idea is to compute a very quick estimate of performance in just 3 to 5 seconds per architecture. So we can accomplish this by just using a single mini batch of data and computing some sort of saliency metric. And I believe the second NAS tutorial will talk a lot more about these techniques. So if you're interested, I believe that's after lunch that the second NAS tutorial will discuss this. Yeah, so in contrast, these are extremely fast, but not quite as accurate as some of the other predictors. Okay, and just one final note. So I talked about many different families of predictors, but in recent work, we actually showed that we can combine the predictors from all these families to have some full omnipotent predictor that can do well in any scenario. And the way to do this is to have some model, but take all the other predictors as input to the model. So in some way, it's sort of like stacking that Alex Mola talked about, except each of these models are like extremely diverse. Okay. Yeah, so with that, I covered search spaces, black box optimization, and performance predictors. And that is the end of part 1. And now I'll hand it off to Day, and I'm happy to take any questions while he's setting up.
Oh, yeah. Hey, thanks for your talk. So you had this one slide where you showed a FissionNet paper and said, yeah, they did it partly manual, partly, but they designed this building block. You also called out that we really want to design architectures from scratch and really discover new components. In fact, some people have called that the holy grail of neural architecture search. And I wonder what direction do you think will take us there?
Oh yeah, great question. Yeah, so as you mentioned, especially on some of the most well-known benchmarks, there still is quite a lot of manual effort that goes into designing the search spaces. However, the holy grail is to come up with like the next transformer, like have architecture search come up with a brand new family of architectures that we have never thought of before, but perform much better. And we still do not have an example of that in neural architecture search. We've had a lot of smaller successes, but not like a brand new architecture. And so one way I think we can start to get there is by searching over both the architectures and the hyperparameters, because it may be that there's a new family of architectures out there that looks so different that we cannot train it using Atom, or we cannot use the normal level of dropout. So I think there's already some work in training, in searching over both the architectures and the hyperparameters.
So one follow-up question, I agree, like the hyperparameters might be one part of it. But do you think we're there yet in terms of the capabilities of the search spaces themselves?
By capabilities of search space, I guess my answer would be that as our search algorithms get more and more efficient, then we will also be able to explore larger and larger search spaces. So like removing more and more of our human bias. So I would say like now we have search spaces that have a lot of like biases, like using convolutions and pooling and things like that. But if we remove them, then maybe there are brand new operations that are better. Okay, so I see a lot of questions.
Right. A quick question about the performance prediction. Are there differences between predicting the validation accuracy versus the training loss, and how do you think about that?
Oh yeah, that's a great question. So there is some work on this actually. There's a Summit training loss paper, and also there are some predictors that take training loss in as inputs and predict validation accuracy. I think the most common way to set it up is to predict validation accuracy, because this is most correlated with test accuracy. But of course we cannot use the test accuracy in our search. But yeah, there are more intricate ways of doing this. We could also do something with cross-validation, or even break out of the bi-level optimization framework. I think we have no more time for questions. Yeah.
Awesome.
Or maybe one more question while we're doing the final setup.
Hi, thanks for the talk. So you talked about exploration versus exploitation trade-off, and I was wondering how did other people look at encoding like inductive biases, such as starting with the transformer architecture and seeing where it does from there?
That's a great question, actually, and there's quite a lot of content in the second half of the tutorial on transformers. So I'll leave it to Day then. In fact, that's a great transition.
Right. Well, thank you very much, Colin, for a great first part. And hi, my name is Debadeepta Day. I just go by Day, and I'm happy to talk about the second part of the tutorial. And thanks for all your questions on chat as well. So Colin will take over monitoring chat. So people who are watching remotely, please feel free to engage, and we will. So this is our current roadmap. I'm going to spend some time talking about Pareto frontiers and the power of Pareto frontiers, and why I consider that important, and also a little bit of an open area of NAS research. It's not as heavily published in and studied as other areas, and then you will see why that is also important in real life. I will touch very briefly upon weight sharing methods, but you will learn in great detail about weight sharing methods in part 2 with Martin and Tejas's talk tutorial right after lunch. So I would encourage you to go there. You will get the whole bucket of all the pros and cons of weight sharing, but I will just introduce it and touch upon it so that I can talk about the other stuff. We will do a whirlwind tour of all kinds of new transformer-based search spaces, right? And this is basically the last 3 months of archive, right? And it probably is already out of date. Sometimes I'm afraid to check archive in the morning because it's just the space of papers and ideas coming out is relentless, especially in NAS. I'll show you a little bit of our work in Petri dish on why it is a different way to algorithms you might have seen before, and is also an example of a Pareto frontier output algorithm. If nothing else in this tutorial, you take away is just take away the reproducibility, fair comparison, and best practices. That's what I entreat you. Forget about everything else if you don't have the attention span right now, and that's what I'm going to spend a lot of time on, right? Because this is just important for the field. And I will spend also a little bit of time on what I consider as interesting open problems. It's definitely not an exhaustive list. And so yes, my personal bias will be there. But just to touch upon some things that are definitely open in NAS research right now. Okay, without further ado, the power of Pareto frontiers. So what is a Pareto frontier? Oops, this is different. Never seen this before. Okay. It's somehow Zoom is not showing the graph. Okay, so which is just should be a screen share in PowerPoint. Let me just end the slideshow for a second and restart it. This is very weird. Give me 1 second. So it's okay. PowerPoint slideshow. Okay. Okay. Yeah, I don't know why I can't. Oh, yeah.
If you want the PDF version, I have it. It's like
Okay.
already up. You could even put it's on my website. Then.
Yeah. So
or you could just
okay.
Like my website. So this is the PDF version at least. And
Okay.
You can present it. Or if you download it.
The screen. The problem with that is yeah, it won't. No, the problem is it won't. Okay, we'll just go back to. No. But I can't give it. Yeah, the figures are not showing up when I share PowerPoint. Yeah, no figure shows up. Okay, so let's try your screen. Yeah, let's make yours. How do I do this?
Let's use but do we want to go into so okay, is it showing up on?
Yep. Wait, how do we minimize that? It's not. I'll put that on the side. Is that good? Okay. Sorry for the technical difficulties, but now that we're back in person, all our projector problems are back. Okay, so power of Pareto frontiers. Oh. Yes, power of Pareto frontiers. So what is so the Pareto frontier word just means it is the optimal trade-off curve, like between multiple objectives. And usually when you are trying to do neural architecture search to figure out what is the right model so that I will deploy it on my device or my service, you are trying to trade off between, let's say, inference latency or peak memory footprint, which is important on mobile devices, and and of course your task accuracy, right? Whatever your task is, you want it to be perform very well, but you want the model to be as small as possible or as memory efficient as possible on your particular device. So if you have the Pareto frontier, you get to then pick which one you will put on which device. Okay, and another scenario where you get to also benefit if you have a Pareto frontier is even on the same device, you may decide that, hey, if there is the CPU is, let's say if you are on a desktop or a laptop, is completely free and I have a lot of compute available, then I'm going to use a very powerful architecture which is bigger. And then if I have a lot less compute available to me and the CPU, because the CPU is suddenly getting used by other background processes or apps, I will switch over to a smaller architecture. And you can only do this if you have the Pareto frontier, because otherwise you don't know which one to switch to, right? What is the optimal trade-off in your search space? So, and note, while I was talking about Pareto frontiers and deployment on IoT edge devices to, let's say, your beefy server in the cloud, I never talked about model compression. I never had to use that term, so which is very nice because I can view model compression. I can subsume all model compression techniques like quantization-aware training, sparsification, everything inside this search viewpoint, right? Pareto frontier search viewpoint, and that tends to be a good viewpoint to take if you are if you have high business value machine learning pipelines that you want to optimize. And the nice part is, and this is I'm giving you an example from one of our works of what an actual Pareto frontier looks like. Is it will look something like this, where every blue dot here is an architecture, and it tells you what the optimal trade-off curve here is. So you can search once, get a Pareto frontier, and decide which one you will put where or which one you will use under what compute availability. And one thing is that the vast majority of papers that you will come across, they do not output Pareto frontiers, right? And I want to be very, very specific here, and this is actually important, is that if you combine, you will come across papers which will have task accuracy, let's say objective 1 plus lambda times objective 2, where objective 2 may be like something like inverse of latency or something which will set up like a log barrier method, which says that if you start going towards your constraint, the objective will go very high, so you will try to minimize both at the same time. So I can subsume all that under this keyword scalarization. I'm going to take multiple objectives I care about. I may have even 5 or 6 objectives. I just add them all up, lambda 1, lambda 2, lambda 3, add them all up and create a single objective. But note, if I optimize that objective, the output is still a single architecture, which is the optimal with respect to this new objective function. It does not give you multiple outputs. It does not give you a Pareto optimal curve. And so this is something to just keep in mind. And this can also be a source of contention when you write Pareto optimal outputting papers, and then your NeurIPS reviewer is like, but compare it, give me a table, right? And I will show you this is the problem you will run into. So you will have to do some reviewer education on the fly. And you may be wondering, we have so much literature which is already coming out for doing single objective or even like single objective via scalarization search techniques, like all the search techniques that Colin just talked about, like bananas and variants of BO and all the evolutionary search. Can I just plug and play that? Do I have to now reinvent completely new algorithms? And the answer is no. You can absolutely plug and play with the existing crop of search algorithms, efficient search algorithms, and create new classes of Pareto frontier hunting search algorithms. So I would very much recommend you this particular paper, because this gives you a bag of baselines, right? These are obvious things that anybody should do if they care about outputting Pareto frontiers instead of a single architecture as an output, right? And if you are thinking of coming up with a new search technique, you should at least be able to beat the bag of baselines here. And the bag of baselines here are very straightforward, very simple to implement. They actually have good implementation out in NASLib or the AutoML library from Freiburg. So you should at least compare against these ones, right? Or at least know about them and why your algorithm is different. Okay, I'm going to move on very quickly in the interest of time to just talking about weight sharing methods. So what is weight sharing? So weight sharing is, I'm sure if you are here at AutoML and if you have done any NAS research or read any paper, you would have come across this idea, right? And then one of the early papers which introduced this idea was the what is commonly known in NAS literature as ENAS, right? Like efficient neural architecture search. And what ENAS did is they introduced this idea of a supergraph, right? And you will hear this in literature term like supernet, supergraph, mothernet, less often, but this is the main idea, is that I'm going to take all the architectures in the search space and I'm going to fuse it into one single large graph, right? And then this graph contains all the exponentially many architectures that are there in my search space. This graph is large, it's memory hungry, but if I can just deal with this one large graph and optimize this particular graph, then I'm good, because the cost, the vast cost in neural architecture search is the cost of doing forward prop and then back prop over all the potentially trillions or hundreds of trillions architectures in your search space, right? So you can see in this that if I just take the architectures which are in red, I just follow the arrows which are in red, that's one particular architecture in your search space. Whereas, and if you just take the list of all possible DAGs and combine them, fuse them all together, then it's very nice, because if I can somehow train this one supergraph such that the rank, the Spearman correlation or Kendall tau with respect to the underlying thing that I actually want to optimize, is that if I had taken each one of these graphs, pulled them out as individual architectures, trained them to convergence, so let's say 600 epochs on CFAR10, and then come up with their ranks of ranked them in order of latency as well as task accuracy or whatnot, I am able to approximate that rank to a high fidelity by doing this weight sharing trick, where I'm now sharing weights between all the graphs which are common, all the edges which are common, right? And this may seem a little bit barbaric, but this is on one-shot NAS, the class of NAS literature you will come across where this supernet idea is used all the time. It tends to work, but there's lots of caveats, and I'm sure Martin and Tejas are going to get into a lot of detail on how to train this beast, right? And the training this beast is not easy. It's also not easy for arbitrary search spaces, and you will see as I go through some of the kinds of search spaces that you could have, that it's not obvious how you will fuse together architectures which differ drastically, right? It all depends upon the granularity at which you are searching. Okay, so yes, attend the next part for in-depth. Okay, one thing I wanted to touch upon, but in the interest of time, I will just show you at a very high level, is one of my favorite weight sharing method. And again, I will skip all the details, but the main idea is you train once for all, and that's why it's OFA. So this is the word you would come across in neural architecture search literature as the colloquial reference to this particular paper. And what the authors did is that let's embrace supernets. Let's just pretend that, like, I'm going to put all my compute that I have available. And in this case, I think it's many 100 hours of A100 or like V100 GPUs on AWS to train a gigantic supernet, fuse them all together. And once this just trained supernet is there, anytime somebody comes and tells me, give me a good architecture or a good Pareto frontier of architectures for device X, and where device X could be a Snapdragon 888 CPU with an NPU on it, or your device could be iOS 14, like, coming out, iPhone 14 coming out in September, and give me the best Pareto frontier for those devices. Now, all you have to do, now that you have this trained supernet available to you, saved on your disk somewhere, you download it, perform search on it, and come out with the Pareto frontier or single objective, whatever thing you care about. And so the cost of, this is why the name is once for all, is that once you have trained the supernet, you don't have to worry about, like, training it again. So the cost of this is costly, it's expensive, needs a lot of tricks and clever, like, engineering to manage the memory of the supernet. You have, you can amortize it, right? So if you train this once and use it 10,000 times, the marginal cost of that is going down very drastically, right? So that's the idea. And you can take in different hardwares and constraints. I'll give you a very, very quick sketch. So one of the things they do is they train such that you take the largest thing first, train it so that you warm start the supernet, and then you slowly, come down and zoom into all the smaller architectures that are in there inside the supernet and make sure they are also getting trained, such that you are trying to compete against if all the subgraphs were being independently trained. Like, you want to minimize the discrepancy in ranking, especially you would have if you had the compute to train all of them independently, but which you don't, right? So that's why you have all this, like, complexity in training. And so here's some progressive shrinking that they do. They shrink along 4 dimensions. So the first one is like kernel. So this is mostly, so in this particular paper, they're doing it for CNNs. So if I have a 7x7 filter, in order to extract a 5x5 filter, they learn a transformation matrix. And so this is all learned as part of the supergraph training, and then so on and so forth for 3x3, right? And then also they do depth shrinking, where the pathways slowly get, like, in the beginning, you train across all the layers of the supernet. Over time, you start getting rid of some of the supernet and diverting traffic out, such that the smaller architectures also start getting trained well, right? So that if I were to extract a smaller architecture, it would also know what to do if I were to force it to make a decision at this layer, right, as opposed to this layer. Because in this one, when I'm training this, it only knows how to make decisions here. It doesn't know what activations I should learn here and what weights I should have in order to make decisions at this step, right? So this is what you are doing, is you're making the supernet be, like, able to give outputs at almost any subgraph that you extract from it, and compete against if you had trained that subgraph from scratch. Okay. And then other tricks, like, how do you shrink down your channels over time? And then at the same time, important detail in blue, use distillation to guide the training of smaller architectures, especially against the big architecture, the supernet you have already been training. And as you can see, this is as published in the paper, the phase 1 cost, like this particular, like training your supernet, is 1,200 GPU hours, right? But that's okay if you believe in the paradigm that once I have this trained supernet, I can just take it and do the search many, many times over without doing this repeated training ever again. And this is where the fun part comes in on how do you do search, right? So if I give you now a CPU and say, hey, give me an architecture that is the best at, let's say I'm not asking you a Pareto frontier. Give me the best architecture which has latency of 10 milliseconds, right, for this task. And first, what you do is you sample 16,000 different architectures from your supernet. This is super easy. You just sample them because you have all the weights, and train a small neural network to predict what this accuracy will be of each of these super networks on the given architecture as input. And that you can do because you can just do forward prop, right? Like, and forward prop is super easy. It's like on the 16,000 architectures to get what their accuracies are. No more training. Backward prop, remember, is the expensive part, is the expensive step. I'm just going to sample 16,000 architectures, score them on the validation set, and train a small neural network to predict for me what these output values would be. And then at the same, and I would train another small neural network to predict the latency given the architecture as input. And this is again super easy because measuring latency is relatively very quick as opposed to training an architecture, right? I don't even need a trained architecture. I can just randomly initialize it as long as there is no conditional computation going on in the architecture. I can go and score its latency, right? And this will take you about 40 GPU hours. Not too big deal given the 1200 GPU hours you have spent on training the supernet. And then now you can do search on a laptop in minutes because now you have this simulator. Remember these, they call it neural twins in the paper, but this is your simulator. This instead of now even invoking any architecture, you run search. And let's say I'm going to use Colin's bananas, right? Or multi-objective bananas from the bag of baseline's paper. And you don't have to use the search that they said. They picked a particular search algorithm. I can plug and play any search algorithm I want, right? All the way from random search to sophisticated multi-objective bananas. And all I have to then do is whenever, in search, you sample an architecture and then you try to get an estimate of its accuracy, you just ask that neural twin, the regressor, hey, what would this give you, right? And it will tell you that, hey, this will give you this particular value. And it may give and if you are smart, it may even give you an uncertainty. So you can take that into account. And since now you have this two tiny neural networks, one for latency, one for accuracy, lying around, you can run search on a laptop, right? Not a problem. In a few minutes, and you can get good results. So this is also a good segue to giving you a worldwide tour of transformer-based search spaces. I wanted to just give you this tour because as a part of not just giving you tutorial about the fundamentals, but also what is happening, right? And right now, in this age of where transformers have been, CNNs were great, RNNs were great. Now, in the last 5 years, transformers have come to dominate, especially all the large foundation models, language models, multimodal models. And so the first one, which is basically OFA applied to a new search space for doing machine translation. And when machine translation, if you have read the attention is all you need paper, that was the original task they introduced the transformers with. And there's an encoder and a decoder. And again, the idea here is I'm going to train this supernet, right? And just like in OFA, if I'm going to apply OFA here, I just need to figure out first, what is this weight sharing super graph I will have for encoder-decoder architectures, where I assume that this is a transformer-based architecture. And we will talk about this later, how much inductive bias you are putting in. Smart people came up with transformers as a manual architecture layer block. Now we are going to try to see whether we can search the backbone of it, right? So the things that are shared, embedding dimension, a number of heads in each layer in your self-attention. Is it 8? Is it 12? Is it 9? Right? Some set of values. What is the hidden dimension of the feed-forward network, right? So the original paper used some magic numbers. Is that the optimal? Then they also relaxed what you attend to. So in the original transformer paper, the cross attention was with the last layer, the last encoder output. But they said, why do we need to attend to the last encoder output? We can attend to anything in between. Let NAS tell me what to attend to in between, right? And or what combinations to even attend to in between. I can have a weighted output, right? And let me not hard code that. And same weight sharing things happening on the decoder side. So that's another idea of a search space, but then you take it and do OFA, exactly what you did before. And now you have this pre-trained super graph, and then you can do search many times over. In our work, we also have found this training. We took advantage of some scaling laws. I won't get into the details of the technique, but again, this search space is very similar where so this is a decoder-only model. Think GPT instead of BERT or encoder-decoder models for NMT. The idea is that what should be how many layers should you have what should be the inner dimensions of the feed-forward network, what should be the D model that you should have. And if I just like start stacking these things up with a few choices for each of these options, you will immediately come into search spaces which look like 10 to the power 34, 10 to the power 50 even, right? And where you allow each transformer layer to be different. And so that's another example of like, you can think of this as transformer backbone. It's still a transformer, but you are trying to figure out what should be its architectural hyperparameters. This one is a very interesting one. So this is Primer. Primer, they did, again, for language modeling. And think about weight sharing while I describe you this one, right? So this one is going to stretch your brain a little bit because it's not obvious how you are going to do weight sharing. Here, this is what I call this as the program synthesis viewpoint of neural architecture search, is I'm going to search over all possible, let's say 12-line programs that I can write down using PyTorch or TensorFlow, right? All PyTorch TensorFlow primitives are fair game. So if I just take the DSL, the domain-specific language that PyTorch or TensorFlow or any such deep learning framework gives me and start writing programs randomly, I want to like just compile them and treat them as my model.py file. So I'm going to, obviously you are going to, most of these won't even compile and be valid programs. You will get errors, but you will have to throw them all away. And then you will have to do special tricks to make sure that most of the time you are sampling valid programs. But if I can do that, then I can like, come up with like very expressive, right? So note here, I'm not going to say the word use self-attention or convolutions as a primitive. I'm just going to say that, hey, I don't know what is the right primitives, right? So let it all come up from like very granular mathematical operations and let's see what comes up. Let search tells us a new kind of architecture. One of the hard part, as you can imagine, that this search space is massive, right? Like I don't even know how to like, I will have to do some math to figure out what is the size of the search space, but most of the things won't compile. And in fact, if you read in the details of the paper, they actually had to seed the search with transformers and whatnot for the search to start working, because otherwise learning was not happening. Search was not happening very well. But very interestingly, they found like, architectural artifacts like ReLU squared. Like instead of where, in the transformer, if you have a text generation model like in GPT, just turn ReLU into ReLU squared. And that performs really, really well. And there was another one, I forget, but, and we tried it in our internal code bases at Microsoft, and actually that works. And we were pleasantly surprised. So even though they didn't find the next generation of architectures, they found interesting architectural artifacts that you could just readily plug and play into your own code base. So that was really fun. Okay, I will skip some of these, but all the like these interesting search spaces are there. So this is NASBERT. Again, like a chain structured search space. Search, like at every layer you have different operators. AutoTinyBird. So this is again similar to the hat paper, but only applied to like BERT. Encoder only architectures. The idea of weight sharing is back because now you are not too granular. Autoformer, similar idea, but again applied to images, image patches. So all these ideas need not just be for NLP. Transformers are there in Vision 2 now. So this is again for Vision. And then what they did is like, hey, why should we just do transformers in Vision and discard all the inductive bias from convolutions that we have had all these years? Convolutions tend to work very well. They're efficient. And if you see like, G equals, so here what they do is like, each time you have a transformer layer, so let's say you have a budget of 8 heads. Why are all the 8 heads self-attention? What if I make 2 of the heads convolution, 2 and 6 of the heads attention? And what is the right mixture of these in each layer? Let NAS tell me, why should I write that by hand? So that's the search space. So global, local blocks, L is local because convolutions they're interpreting as local operators. Transformer, self-attention are global. They're working over the whole image at a time by looking over all the patches. So that's another interesting search space. Yeah, so these are all there. I will skip some of them. I will skip actually the Petri dish slides, but feel free to go over them. I have talks on Petri dish before because I want to spend really time on this, right? So as I promised, like this is really, and I know we are running out of time, but I want to spend just 5 minutes on this. Reproducibility, fair comparison, and best practices. So, and sure, if you're sitting here, I'm sure you have when you have read NAS papers or any kind of AutoML paper, many times you are wondering, this is such a complicated pipeline. Why does this work? What part of this is important? How can I reproduce this easily? Even if, and it's not as easy as like, is source code is available. Yes, source code is available. You can go and run it. But what if you don't have TPUs? And what if your GPU is different? So you cannot fit the same batch size that the authors did, right? And there's a lot of stochasticity. What if I have used, when I published my paper, a training routine, which on CIFAR 10 uses 1500 epochs of training, and then other papers use 600 epochs of training. So in NAS, like, the training routine is usually held constant in NAS papers, unless you are looking at a NAS plus HPO paper. So if my training routine has all the tips and tricks, right? Like I put auto augment, cut out, cut mix, you didn't. So your architectures may just be underperforming because it just doesn't have as fancy training routine as mine did, right? It has nothing to do with your search space or your search algorithm. So this becomes a huge problem in comparing papers. And that's why you will find papers like NAS evaluation is frustratingly hard, right? So as Colin mentioned, benchmarks are to your rescue. Like, try to use benchmarks as much as you can, unless you are trying to run NAS on a completely different. So for example, one benchmark which is missing right now, a glaringly obvious one. So if there is enough interest in the community, is a transformer-based, like, search space, right? Like we would love to have a benchmark which is has self-attention and whatnot in it as well. And have that make it available to the community. So if you're interested, reach out to me. I can provide compute. So NAS Bench Suite, as Colin mentioned, is a nice one because it unifies a lot of NAS benchmarks through one interface. So I highly recommend you use it. But yes, there's tons, and I think Colin had a way more exhaustive list than this one. Before you start your project, and this is, I beg you to just read the NAS best practices checklist, right? Like, just read it. If you have, and what I strongly recommend is to read the journal paper. But this was actually, like, you would be surprised when you go read through this. It will inform your projects and your experiments and even your ideas, like, where do this resist stand? How I'm going to compare, how I'm going to evaluate before you go and spend all the compute in the world, especially if you're not using benchmarks, because a benchmark doesn't apply to you and you are using it on new problems, and spend compute. Think of how you are going to do this beforehand. So it'll really help you keep good logs, architect your code well, and also measure all the times and compute cost properly. Take advantage of NAS frameworks wherever you can. There's a couple of ones I will mention. So NASLib, this is from the Freiburg group, and one which is from my group. And both of these, none of these are hobby projects. So don't worry that, oh, people will abandon it. Nobody will take advantage of your pull request. You will not get credit. So I know that, like, NASLib has a large lab. Frank Hutter's lab is backing it, and others as well. My group now has like 8 full-time research engineers backing it. And we are going to have a big push release coming out very soon. We're ramping up. They all have like different pros and cons. I won't get into that for now. But consider using and contributing and making your code via pull requests and etc. GitHub issues available. It helps everybody out in the community and helps us do better research. There's a couple more interesting one. AWNAS is a good one. And then PyGlove is also interesting because they do like symbolic programming. So you can define search spaces via symbols and then do also search over it in a program synthesis like manner. So that's definitely an interesting twist. And you may be wondering, is NAS solved, right? Like, should we just go home tonight after our dinner? Obviously, the answer is no, because we are just getting started. There's lots of domain knowledge. Like, as you imagined, like, how are we going to invent the new architecture? Like, one of the things I think NAS doesn't have a big win in the community right now in deep learning is we, as a NAS AutoML community, haven't given rise to a new large foundation model, or at least one that I would think of off the bat. We have done very good on what I would call the right-hand side of the Pareto frontier, on efficient models, efficient net, NASnet, all these, like, models are there which come from NAS. How do we go into the large next side, the left-hand side of the Pareto frontier, the foundation models, the big one, the Palm, the Gato, the Megatrons, all these Turing? How do we create that from NAS? And I think there's a special session tomorrow on large language models and foundation models and NAS. And I think we need to come together as a community to think of how we will do that, because obviously that's way more challenging. It's difficult to train even one of those, let alone many times. In most NAS paper, hyperparameters are magic constants. And which is why, and I think people were, somebody asked this question in the first one, is when you are doing search, right? Like what if every architecture may have required a unique set of hyperparameters, a unique learning rate schedule, a different optimizer, right, than what I used, which is held constant usually during search. So what are we going to do there? And yes, this is difficult, and there is evidence, at least qualitatively, to believe that our optimizers are co-evolving with our manual common architectures, right? So this is a problem which is inherent, that the moment you switch away, like your transformer, to a different architecture and your LAMP optimizer doesn't work with it, right? So if you use like the NVIDIA Megatron code base, the LAMP optimizer is there with very nice hyperparameters. The moment you change it even a little bit, things switch out. Architectures don't perform as well, and the ranks of architectures in your search space will differ drastically. We tried it with NAS Bench 101 because we had to recreate it from TensorFlow into PyTorch, and then we don't have TPUs, we have GPUs. And then instead of RMS prop, if I use Adam, the ranks of architectures from the bottom 25% can flip to the top 25% and vice versa. And I have not tried this on others, but if you try it, let me know. Another problem, which, and this is the last one, so last 2 minutes before lunch, is there is this another revolution which is happening in the deep learning world today, right? Like especially perhaps in the more on the industry side of things, is how do you actually deploy a model? Like nobody deploys their PyTorch model, nobody deploys their TensorFlow model directly, right? You are going to quantize it. You are going to use something called a deep learning compiler. Examples of deep learning compiler are like OpenVINO, TensorRT, TVM. So these are all like deep learning compilers that will take in Onyx, also can act as a compiler, but it's more like a runtime. But all these compilers, they will take in your model and they will produce highly optimized code that the machines can execute without your framework anywhere being in the picture, right? And this is important. Nobody will actually take a PyTorch model and deploy it, right? Even a quantized PyTorch model. So you are always going to do this. And here's an inherent problem, and this is something we found when we were writing Archi and working with our product groups. If I take any state-of-the-art deep learning compiler, and if you open up the deep learning compiler, they have got manually coded pattern matchers for common architectures. So they will detect that the moment you input a PyTorch file or a TensorFlow file or an Onyx file, they will detect, oh, there is a transformer layer in there, and all the transformer layer specific optimizations, which they have hard coded, will kick in, right? Or they will detect, oh, this is a resonant block. I know this is a resonant block. Great. I'm going to put in all these hand coded optimizers suddenly become active, right? So they will know which ops to fuse, which ops to distribute, which ops to put where, how to optimize memory. All that stuff is done in this hard coded pattern matching manner. And by pattern matching, I don't mean machine learning, but just hard coded if then else statements are there if you open up the code. So which means if you run Pareto Frontier search or any kind of NAS search with one of these compilers in your inner loop, like where you are taking them, you are getting the latency or memory footprint of your quantized compiled model, very often you will find on your Pareto Frontier the same the manually tuned architectures showing back up on your Pareto Frontier, right? And why? Because those ones have special treatment. So there's this other thing is latent problem is when we are going to do NAS, especially for deployment scenarios, we need to figure out how we can make the compilers also expressive, right? And there's work like auto TVM, auto scheduling that exists. OpenVINO also has some auto scheduling work there, but this is a bottleneck that people often don't think about when you're writing a paper. But when you go to deploy things and you put this in your inner loop, you will find that wonky architectures, the weird ones, your NAS comes up with, they actually will not show up on the Pareto Frontier because of this inherent problem, underlying problem in the compilers. that's it. And if you have any questions, we are free for lunch, but I'm happy to stick around and answer questions. Please. Mm-hmm.
Sorry, just for Zoom.
So first, a very nice tutorial. So earlier you mentioned we can also use NAS for optimizer. So, and we can use like a similar HPL approach to optimize for hyperparameter. But optimizer, people also use neural networks for the optimizer.
Yeah.
Then those neural networks further introduce more hyperparameters.
Exactly.
And to optimize those hyperparameters, you introduce even more hyperparameters. So my question is, when do we know we should stop?
So this is a very, very big question, right? Like, so for example, in the bananas paper, Colin uses for example, not Colin, like somebody else has used like graph neural networks to encode architectures, right? And now the graph encode, your encoder itself can be hyperparameter optimized, right? So now you are starting to hyperparameter optimize your NAS algorithm itself, right? As you point out, and another thing. So this is an open problem. Like, where do we stop? Like, how do we make optimizers which are also adaptable? And we can be confident that they will be able to extract performance out of every weird architecture to the best that it is latently inside it. I don't know. I think this is where deep learning optimizers need to make advances as well, such that we are not co-evolving optimizers only for the RNN or the self-attention or the CNN block and the patterns that we use them in. Yeah, open question completely. I can be around, but I don't want to hold other people up. So feel free to, yeah.
So thank you both for your talk. And I have a question about the surrogate models. So when you have surrogate benchmarks, then how do the surrogate models itself get benchmarked? Because
Colin, do you want to take that on?
Because there could be like some bias to the surrogate model that is used in the benchmark itself.
Yeah, it's a good question. So that's the surrogate benchmarking paper by the Freiberg group, and I think they actually did a very good job and really extensive testing how well it does in certain situations, because they got these types of questions a lot. So a few things I remember they did were, one, they had a lot of diverse training data. The most training data they had were random architectures, but they also had stratified samples, like architectures found from different popular NAS algorithms. They also ran other experiments like testing the model in different subsets, like only allow certain operations and things like that. They also, I think another experiment they did was like check what the best predicted model is using the surrogate, and then train that model and neighboring models, and then add that as training data, and then seeing if there's a new best, and then like reaching convergence that way. So yeah, they did. But yeah, I think they also do recommend not using their surrogate to test algorithms that use the same type of model. So they released a few different types of models as surrogates that can each be used.
Okay, thanks. Maybe one quick question, because in the benchmarks you have all the data about accuracies and so, but right, there are no checkpoints of the networks, and I wonder if there are some were saved or if they are just discarded. Because I wanted to look like what the output of the network is, and had to train the networks myself, and there's not much code about that.
Yeah, I think so. As both Day and I showed, there's quite a lot of NAS benchmarks. I believe some of them do save the checkpoints, but yeah, I was gonna say 201 too. Yeah, it is it's very a lot of memory to save it. So not that many works do save it. I mean, even 201 is like the smallest one. I think it's terabytes. But yeah, there are some out there.
Thanks.
one more.
Yeah, thanks for the great overview again to both speakers. To find novel architectures from scratch, the previous speaker mentioned joint architecture and hyperparameter search as one of the most important points, and you also mentioned it during your talk, right? Yeah. But do you agree that it's the most important point or one of the most important points? And what else would you want to single out here to reach this holy grail of NAS?
Colin, feel free to also chime in and with your thoughts. I would say, so if that's, other than that, what would be a good search space? I think what is the granularity of search space you want to search in is a very open problem. As you can tell, like, if I make the search space like the list of all TensorFlow programs, this is going to be very difficult to search in. And when Google had mixed results searching in there with their vast compute, and you can't really do weight sharing. Like, you can't do weight sharing very easily when you are searching over primitives at that level. So this is a very open problem, like how much inductive bias to give in to your search space and how much to leave to the search algorithm to discover, so that you can also discover new things. It's not easy. I gave you a preview of lots of different search spaces, and they each will have its own pros and cons. And yeah, so this is an open problem worthy of consideration.
Yeah, thanks for the excellent answer. When do you think will we get there?
I think that, I'm always really surprised. I'm not going to make predictions, but so for example, Amit Alwakar's group and Chris Ray has this really nice paper that I like, this NeurIPS on like diverse search spaces, where they define this like optimization problem, where the different solutions to the optimization problem are different operators. I really like that style of work. So it's like more like a generalization of Fourier transforms for defining operators. So I can see some spark of new ideas coming in. But yeah, not maybe in 3-5 years, but I could be wrong. But this is being recorded, so we can come back. Yeah. I think maybe perhaps we should let people go to lunch, and I'm happy I'm around, and Colin is too. So we're happy to discuss and meet people. Thank you.